Quantum mechanics is the other half of physics. In physics, there are three fields that deal with explaining the general reality of why objects move and behave the way they are. On one hand, we have general relativity theorized by Albert Einstein, classical mechanics, and quantum mechanics. Quantum mechanics deals with the size of the very small, which includes particles such as electrons, photons, which are packets of light, and the various quarks that are part of a subset of subatomic particles that constitute protons and neutrons. It is at the subatomic level that the laws of classical physics no longer apply, and particles would often behave in a counterintuitive way. A spin of a particle is usually related to the interaction with the magnetic field. Just as the computers we have today have two types of data, called bits, which include either a 1 or 0. A quantum particle may have two spins up and down. Not only that, but the up and down spins can exist at the same time, especially before the spin is measured. This implies that a quantum computer using a qubit, quantum bit, may perform two calculations at the same time. Whereas computers we have today can only perform either one of the calculations. The result is the massive decrease in time to perform calculations and the increased capability of performing complex operations. Particles can also become entangled. When two particles become entangled, if we know the spin of one, we can know the spin of the other, even if the particles are long distances away from each other. Entanglement is useful since particles can act like logic gates in a computer, thus able to show and or not true and false. Quantum particles rely on probability. Despite particles can be in a superposition state, the result of getting a certain spin is determined by probability. Decoherence is a state of maintaining a particle to behave in a quantum mechanics-like fashion. An electron, for example, may be in superposition state for a short period of time. However, trying to observe what state the electron is in may put the electron into decoherence, as the superposition is broken. It is extremely difficult today to maintain a superposition in order to perform simultaneous calculations, but even so, the answer calculated will be a probabilistic state, and thus more runs are needed to verify the answer. Quantum computing is currently in its early stages. Right now, only a few atoms, around 7 of them, has been used to test out quantum computing. The main obstacle that is getting in the way is the issue of decoherence. Very little has been done to eliminate decoherence from occurring. Quantum computers have been using extreme low temperatures in order to operate. Factoring large numbers is an essential part of encryption. Encryption sets up codes so that information cannot get accessed by hackers and thieves. This is especially important in regards to online banking, confidential government documents, and maintaining internet security protocols so that users can remain anonymous. A drawback though is that passwords may be easily hacked since quantum computing can essentially crack a vast number of passwords in a little time. This poses a new challenge in how to protect account passwords. Quantum computing may speed up the use of algorithms implemented in machine learning. Machine learning allows a computer to learn by itself through predicting future algorithms. Suppose you write a program and the figure is learning how to kick a virtual ball on the screen. The figure would be in the first few attempts, trying to guess the placement, timing for the ball kick, or time it will, based on the prediction algorithms, teach itself to kick the ball. Artificial intelligence, or AI, utilizes machine learning without humans to directly program them. Of course, this is also in its early stages. As development in artificial intelligence machine learning accelerates, we may be able to see robots with a will of their own.